Hello and welcome to today's tutorial. So today we're going to talk on the examples of addition and multiplication of a random process that we have seen in the last tutorial, and if time permits we will even cover the ergodic random process. So let us switch back to our screen and let us revise what are the addition and multiplication random process will result in, and then we will quickly look into a few examples. So from the previous tutorial, we have discussed the addition of random process. If you add the two random process, what does it relates in terms of its autocorrelation function? So we obtained an equation that is Rw of tau is equal to Rx of tau plus Rxy of tau plus Ryx of tau. Sorry, this is Ryx of tau plus Ry of tau, and if this is equal to nothing but the mean of x with mean of y, because it results in a cross correlation, and if any of this mean is equal to 0, so then that Rw of tau is equal to Rx of tau plus Ry of tau. So it means it is an addition of the autocorrelation of two random process will result in new random process, that is Rw of tau. And if you multiply the two random process, then its autocorrelation function is also a product of individual autocorrelation function of the process. So with this, now we will look into a few examples here. Now let us look into a few examples. Okay, yes, so let me take this page number 24 here. Okay, so here is an example. So the random process is given, that is x of t is equal to a into cos of omega ct plus theta. So let me write here. So this is given as, that is x of t is equal to a cos of omega ct plus theta. So this is given, is a wide sense stationary process, and here the theta is uniformly distributed over the range of minus pi to plus pi. Remember, whenever here if theta is given and if theta is a random variable and it is distributed over the range of minus pi to plus pi, then it's the density function. Sorry, here this is supposed to be the density function, not distribution function. So it is f theta of theta is equal to 1 by 2 pi for the theta range from minus pi to plus pi. Otherwise it is 0. So this you have to remember it always. Otherwise, if it is 0 to 2 pi also, its density function results in 1 by 2 pi. So now first we will calculate the mean of it. So we know the formula of the mean, that is mu x of t is equal to integral of x into fx t of x into dx, that is nothing but x multiplied with the density function. Now I will substitute the x which is given, that is a cos omega ct plus theta, and the density function from this definition is 1 by 2 pi into dt. So we have to integrate with respect to theta. So now we will going to apply cos a plus b formula here. So that is cos a into cos b minus sin a into sin b. So then we're going to integrate this, so then cos term will remain to be same, and then we'll got here sin. So here we'll get so integration of sin is minus cos okay, it's supposed to be a cos function here, so it is cos, and again sin theta is minus cos theta, so it becomes yeah, so it is a minus anyway, so it is a cos theta here. So let me erase and write it correctly. So integration of cos omega ct is, yeah, sorry, that was correct actually. So it is sine, because here the sine omega ct is a constant. I forgot to tell you, here sine omega ct is a constant. We are integrating only with respect to theta term. So theta integration of cos theta is sine theta minus sine theta and sorry, cos theta is sine theta, and integration of sine theta is minus cos theta, so we'll get here plus. So when we substitute these limits here, so what happens here, this term will become 0, and here the cos pi is minus 1, and minus of cos minus pi is minus of minus, it will become plus 1, so it will become 0. So ultimately the mean, we will get this as 0. So that is what it is written here. So ultimately we'll get the mean of this process, of this random process, is equal to 0. So this is very important example here. So then let us go to the next page here. So now let us find the autocorrelation function of this. So let me save this page. Let us find the autocorrelation function of the same random process. Now we know the autocorrelation function, that is Rx of tau is equal to an expectation of x of t into x of t plus tau. So again we have substituted the same terms here. So we have just interchanged the terms, that is here it is x of t plus tau first we have written, and then we have written x of t term. So fine, there is no issue with that. So now it is, again we apply the formula of say cos a into cos b formula that I have written here, that is equal to half of cos a plus b plus half cos a minus b. So then we will get here, that is we applied the formula here, then we obtain, so a square by 2 I have taken it outside, so expectation of cos 2 omega ct plus this is plus term, so plus omega c tau plus 2 theta plus cos of omega c tau. So cos of omega c tau is a constant in this term. So now when we integrate this term, the same thing, like again here we have to apply cos a plus b formula here. Then when we simplify, ultimately this term will go to 0, like how we have seen for the previous case. The same thing is applicable for this as well. So now here the cos omega ct is a constant, cos omega c tau is a constant term, since we are integrating with respect to theta. So then when we integrate this and substitute the limits for theta, then we will get a square by 4 pi into cos omega c tau, and 2 pi and 2 get cancelled. So ultimately we will get a square by 2 into cos omega c tau. This is a very important example. Now we often come across this term cos, so remember its ultimate solution is cos omega c tau. So whenever we have a cos omega ct plus theta, then we will get this solution. Okay, so now let us go to the next example here. So next we will see what is the example. Okay, so here it is given one more example is that is let we have two independent process here, that is x of t and y of t, which are jointly Whiteson stationary random process. So that is defined here, and the definition of x of t and y of t. So that is a cos omega 1 t plus theta 1, and y of t is b cos omega 2 t plus theta 2. So here theta 1 and theta 2 are independent random variables distributed uniformly from minus pi to plus pi. Obtain the autocorrelation function of multiplication process. So here we are using the multiplication process that we have discussed earlier at the introduction part of this tutorial. So now from the previous example, we will going to straight away use this relation. I'm not going to do again this expectation operation. So same thing. So here the density function is again f theta of theta remains to be same, that is 1 by 2 pi, where the theta range from minus pi to plus pi, and that if we substitute in the expectation part and we apply the expectation for Rx of tau, then we will get that the same process as this, that is a square by 2 into cos of omega 1 tau. And for the second process y, we will get ry autocorrelation function, ry of tau is equal to b square by 2 into cos of omega 2 tau. So this straight away we have drawn from the previous example. So please, if you not understood, refer to the previous example. From that we have got these results. So then now we know that the multiplication of this process is nothing but that is x of t into y of t will result in also the product of the autocorrelation of these individual process, that is Rx of tau into Ry of tau will result in Rw of tau, that is a new process. So now we have substituted these terms here. So when we substitute here, so then we apply the cos A into cos B formula, that is half cos A plus B of here, so plus cos A minus B formula. So when we apply that, so we will get A square into B square by 8 into cos omega 1 tau plus omega 2 tau plus cos of omega 1 tau minus omega 2 tau. So this is the answer. No need to further simplify this or represent in any other form. So this is fine, we can keep it in this form. So now let us see the next example here. Hope you are following these examples. I am not going too fast. So now let us see the next example. The next example is that the quadrature modulated process are given. So here theta is uniformly distributed over 0 to 2 pi, and omega c is the carrier frequency, and here it is asked to find the cross correlation of x1 of t and x2 of t, then show that the theta is orthogonal in both quadrature modulated process. So here we have to find the cross correlation function of two different processes, that is x1 of t and x2 of t. The definition of x1 and x2 is given here below, that is x1 of t is equal to x of t into cos omega ct plus theta, and x2 of t is equal to x of t into sine omega ct plus theta. Okay, so now let us write the cross correlation definition. So rather than writing this as Rx y of tau, because there in the previous definitions we had the two processes, that is x of t and y of t, so we used to write this as Rx y of tau. But here the process is x in both the case, but it is represented as 1 and 2. So we'll write here R. So let me clear this section and write neatly. So we'll write this as we'll write this as R12 of tau is equal to expectation of x1 of t into x2 of t minus tau. So here rather than taking t plus tau, we have taken t minus tau. Anyway, it is both are same. There is no difference at all. Just for our simplicity, we have taken this term. So now if we apply an expectation operator here, and we substitute the terms, what is our x1 of t and x2 of t, so that is x of t into cos omega ct plus theta, and here x2 of t is nothing but it is t plus tau, so it is x of t minus tau into sine omega ct minus tau plus theta. So we have simplified this term, and here it is sine term, so we applied a sine a into sine b formula here. We have taken x of t and x of t minus tau as one expectation, so that we can get rx of tau, the autocorrelation function. We know that from this we will get autocorrelation function, and we have separated the cos and sine term here with an expectation. So we apply this cos a into cos b formula here, so we'll get half sine a plus b minus sine a minus b. So when we substitute this, half of sine, we'll get 2 omega ct minus omega c tau plus 2 theta minus half sine omega c tau. So remember again here we got constant term, that is sine omega c tau, because again we are going to apply this expectation operator. When we apply expectation operator here, our density function is with respect to theta, that is 1 by 2 pi, and theta is a random variable, so we are going to integrate with respect to theta. So again this sine term will going to be 0 when we apply again cos a plus b formula here. We will simplify, integrate these terms, finally it will become 0. So since now we will take only the constant term and integrate this, so we will get this integrated term here. It is a constant, so we'll keep it outside, so we'll integrate only this theta. We'll get so finally we'll get minus 2 rx of tau into sine omega c tau, and if the value of tau is equal to 0, then this cross correlation function will result in 0. So this is the bottom line of this. So final definition is this: we'll get minus half rx of tau into sine omega c tau if the difference, that is we have talked this in the first tutorial of this random process, what is the time difference tau. So tau is nothing but the difference of two time instants, that is t1 and t2, that is written as tau is equal to, let me write here, the tau is nothing but the difference of two time instants, so it is written as t2 minus t1. So if this time difference becomes 0, so then this cross correlation function is ultimately results in 0. So that's it. Now let's see what is there next. So next there is one more example here. So in this example, um, so here the PSD, the power spectral density of the random process involving the n symbol of unsynchronized pulses is given as fx of x, and the duration of the pulse is t seconds. The pulses have amplitude of plus or minus v. So please read it as plus or minus. I could not write it here as a symbolic representation. So read this as plus or minus v, and they are unsynchronized, and they are uncorrelated. So here we have to obtain the mean, variance, and autocorrelation. So this is our definition which is given of density function, that is fx of x is equal to 0.5 delta of x minus v plus 0.5 delta of x plus v. So now let us find the mean of this. So mean is given as an expectation of x of t. Now integrate minus infinity plus infinity. We know this definition. So mean of a random process is defined as an observation multiplied with the density function, that is x into fx of x into dx. So let us substitute the x and fx of x, we will substitute here. So to integrate this term, we should know the property of an impulse. So from the property of an impulse, so integration property of an impulse, that is x of t in delta of t minus t naught, integrating with this with respect to t, so we will get x of t naught. It means we will get that pulse. So if we have some x here and we are integrating with an impulse with some t naught term, so then we will get ultimately we will get that instant of sample, that is x of t naught. Okay, so same thing is applied here. So now it is not x of t, it is just an x observation. So here we will get, when we integrate this term, we will get minus v. So that is what we will get here. We will get minus v, and here we will get plus v. So when we combine this, we will get ultimately the mean as 0. So let us go for and see what is its variance. So yes, so now let us look into the variance of this. So variance, the definition of the variance is a sigma x square is equal to expectation of square of the random process, that is x square of t minus the mean square, that is mu x square of t. We know that the mean from the previous definition, it is 0. So now it is only the expectation of x square of t. So let us substitute here. So it is x square integral of x square into fx of x into dx. So we'll substitute here. So from this definition, again the same thing holds good. Now we will get here, it is not just minus v, it is minus v square, because here we have the term here x square. So finally we will get here the variance of this process is v square. And if you look into the autocorrelation process, then from the definition it is expectation of x of t into x of t plus tau. So when we substitute here, and if we treat this individually, then we will get mu x of t into mu x of t. So both are 0. So this applies on a special condition only if the value of tau is greater than t, the time period t or the fundamental period t. If it is, the tau value is less than t, so then there is a one more definition of holds good, then it is v square of 1 minus tau by t. So this is the definition holds good for this condition if it is partially overlapped. If it is completely overlapped, then we'll get an autocorrelation function as 0. So these are the few examples on the addition and multiplication of a random process. Now let us talk about the ergodic random process. So before, I'll just give the quick introduction of ergodic random process. Then we will actually compile what is it, ergodic random process. So ergodic random process is nothing but if the n symbol average and the time average, if both results in same value, then such a process we call it as a ergodic random process. Clear? So this is basic definition. So now let us see the let us see what is ensemble average, and then we will see what is the time average. Then we will again come back to ergodic random process. So let me write here the what is the ensemble average. Okay, so let me write the definition here. It is the average taken across the process. Such averages are taken at some fixed time instance. For example, we will see for example, let us see the mean and autocorrelation or ensemble averages. Okay, so mean and autocorrelation are ensemble averages. So we talked in the introductory video of random process what is the meaning of ensemble. So let us quickly revise it. So ensemble average is nothing but, for example, here I have some data here for the maybe first day of data, second day of data, third day of data. So this might be a temperature, humidity, pressure. You can take it anything. Like this, I have infinite number of data, and if I draw some time instant here, I'll draw some time instance here, and these points are nothing but forms the sample space of my ensemble. If I add all these and take an average of this, so this is called as an ensemble average. So likewise, I can take for any time instant. So this time instant I call this as t1, and this another time instant I'll call this as t2. Like this, I can take for n time instance and I can average all these. So that is called as an ensemble average. And mean and autocorrelation are the best example of ensemble average. So let us write the definition of mathematical definition of mean. So we know that mu x of tau is equal to, it is integral of minus infinity to plus infinity. It is x into fx of it is fx t of x into dx. So this is the mean mathematical definition, and if you write the autocorrelation definition, we all know that is Rx of tau is equal to double integral of, say, minus infinity to plus infinity. That is, we can write here x1, x2 into fx of t1, fx of t1 into t2 of x1, x2 of x1, x2 into dx1 into dx2. So this is our mathematical definition. If the above two averages are taken across the ensemble at particular instance, so hence they are ensemble averages. So this is about this. So let me save this in a page. So this is 20, 30, okay, so it's a page number 30 here. So now let me define what is the meaning of the time average. So I'll keep the heading same. It is Ergodic Random Process. So let me define what is the time averages. So it is nothing but these are the averages taken along the time. That is, these are also called long-term sample averages. long-term sample averages. Now, in the previous slide, we have seen the the data. For example, this is the some data that we have collected, and this is the another data which we have collected on the second day. So now, if each of these data, if I call this as say x1 and this is say some x2 with respect to these data. So now, if this is with respect to time t, now if I take some instance of one particular data and if I take some points here, the sample points, and if I take average of this, so then this is called as the time average, means over the time I have averaged these values. So this is called as the average time or the long-term sample averages. So this mathematical definition we can write like this, and this we cannot do over a infinite number of interval, means this signal cannot range from minus infinity plus infinity. It means then we cannot do it. So this should have some start time and end time. So this start time and end time is defined by some interval, say minus t to plus t. It means we are going to take only the average within this limit, the start time and the end time of this data, of this one data which we are talking about. So then its mathematical definition, we can define this as mu x of t, the time period or the sample period, is equal to 1 by 2 pi. We are going to average it 1 by 2 pi from minus t to plus t into x of t into dt. So it is straight away, it's a simple integration of the term. It means the term, the x of t should be summable, means it should be integrable, it should be a finite. We cannot do this for infinite, so we will restrict this to minus t to plus t. Or this can also be defined as, that is mu x of t equal to, if limit t tends to infinity, if t tends to infinity, then we can also call this as 1 by t. Since it is, we are taking average of only 1 by t, now our integral limits will change from minus t to, it will change to minus t by 2 to plus t by 2. It is x of t into dt, x of t into dt. So these are my mean definition of the time average process. Now if I look into the autocorrelation process of this, then the autocorrelation process is defined as then Rx of tau comma t equal to 1 by 2t into integral of, again say minus t to plus t into x of t plus tau into x of t into dt. Or this can also be defined as Rx of tau comma t is equal to limit, as the limit t tends to infinity, so then it is 1 by t integral of minus t by 2 to plus t by 2, then it is x of t plus tau into x of t into dt. So this is the time averaged autocorrelation for this time average process. Now let us define this ergodic process. Let me save this page here. So this is page number 31. So now come back to our ergodic process. So let me define this here. So a random process is called ergodic process if time, as I told before, if the time averages are equal to ensemble average, averages. So that is called as the ergodic process. Now if we write mathematically, so then it means it is mu x of t is equal to, it is mu x of t, the time interval, that is t, and its autocorrelation is defined as rx of tau, rx of tau, or rx of t1 comma t2 also we can write. So rx of tau is equal to, it is rx of tau comma t. If this condition is satisfied, then we say that it is an ergodic random process. Now we will see one or two examples on this ergodic random process, then we will wind up this tutorial. So here, before going to this example, I want to highlight one more thing here. So we can say that the process is ergodic in mean if the following condition is satisfied. That is, the limit t tends to infinity, if limit t tends to infinity, then mu x of t is equal to mu x of t, and the second is that if limit t tends to infinity and if the variance of the mean, see this, the variance of the mean mu x of t is equal to 0. So likewise this also holds good for this autocorrelation function. So as the limit t tends to infinity, that is rx of tau comma t is equal to rx of tau, then the limit its variance as the t tends to infinity, then the variance of this autocorrelation is 0. Then the variance rx of tau comma t is equal to 0. The first condition says that the time average condition approaches n symbol autocorrelation as the observation interval, the t, approaches infinity. And the second condition says that the variance of time average autocorrelation is 0 as observation interval t approaches infinity. So here the second term says that the variance of the time average autocorrelation is 0 as the time interval approaches the infinity. So these are the few definitions which we should know regarding the ergodic process. Now let me take an example of this ergodic process here, and then we will try to show this is equal to 0. So let me save this page, and okay, it is not saved, so it is page 32. So let me write the example here, the problem. So it is for the random process x of t, which we'll define below, where a and omega c are constants. So again it is the same example that we have discussed before. We are taking the same thing. Now theta is a random variable uniformly distributed between plus or minus, please read it as plus or minus pi. Show that this process is ergodic. So let me define the x of t here. So the same x of t which we have taken for the multiplication addition example, we are taking the same thing. So x of t is equal to a cos of omega c t plus theta. So I'll take the same thing here. So now for this process the mean of both n symbol average and the time average should be same. So this okay, there is a proof. So we will just do this proof to show that the mean of the n symbol average and the time average is same. So let us take the mean here. Mu x of the time average is equal to, we know that it is 1 by 2t into integral of minus t to plus t with x of t into dt, and let us take the mean of an n symbol, that is mu x of t is equal to an expectation of, sorry, let us take the n symbol of the mean itself. Let us take the n symbol of this mu x of t. Then what do we get? If we take an n symbol of this mu x of t, I think it's supposed to be the capital T here because it's a time period. So n symbol of this t again, so it is so we have 1 by 2t into integral of minus t to plus t, then we have our x of t into dt, which is equal to, we get 1 by 2t is a constant, we'll take it outside, integrate with respect to small t, then n symbol of this x of t into dt. So the n symbol of this x of t is nothing but it is mu x of t. So if we integrate, it means it's a Whiteson stationary process. It means we can write an expectation of mu x of t, this is small t itself, then expectation of t is equal to, it is mu x of t. Okay, so we're not going to find the mean here because it's both the means are same. So we'll look into the autocorrelation process. So let me save this page here, so 33. So we'll see the autocorrelation process here. So from the autocorrelation definition, it is Rx of t comma Rx of tau comma t is equal to the limit t tends to infinity with 1 by t into integral of minus t by 2 to plus t by 2 into x of t plus tau into x of t plus tau into x of t into dt. So now we are going to substitute here these terms. Now the limit t tends to infinity, it is 1 by t into integral of minus t by 2 to plus t by 2, then it is a cos of, we have omega c of t plus tau plus theta into a cos of omega c t plus theta into d theta. So here we are going to apply the formula of again the cos A into cos B formula, and then we will get a final term here as a limit t tends to infinity, then it is 1 by t into integral of minus t by 2 to plus t by 2. So we will get here a square by 2 of cos of omega cos of 2 omega c t plus 2 theta plus omega c tau plus cos of omega c tau into dt. So now we are going to integrate with respect to t. So we know that again this term here finally we will get this as 0. This we have seen in the previous example also. Again we are going to apply, that is cos A plus B formula, then we will get cos A into cos B minus sin A into sin B, and then we will going to integrate these terms, and when we substitute the limits we will get this term as 0. So finally if you look into this, this is a constant, so only we are integrating this with respect to constant into dt, and we substitute minus t by 2 to plus t by 2, then finally we will get this result as it is a square by 2 into cos omega c tau. And if you can recollect this at the beginning of this tutorial, we have solved the same example for the same x of t process, that is x of t is equal to a cos omega c t plus theta. So there though we have integrated with respect to theta, it is same, so we will get that the same result here. This is also equal to our rx of tau in that example, so we'll get the same term. So now the mean as well as the autocorrelation function both results in same thing. So we have proved that this process is an ergodic process. Okay, then thank you for watching this tutorial. In the next tutorial we will solve few more examples on this ergodic process, and then we will talk on the power spectral density. Thank you for watching. Subscribe to the channel. Thank you.